Part 3 of the presentation. Now that we have discussed the various inputs, we're going to go over the relationship between the log file and the loads in plan view. The log file is created when you generate loads and provides details for all the wind and seismic loads generated. After generating loads, but before running the design of your project file, the log file will only include details of the wind and seismic load generation. But after you run the design, the log file will also include details of the torsional analysis completed for rigid diaphragm distribution. Log file includes details for all the equations used from ASC 710 and summarizes the forces generated in each direction in a table. All the details for the torsional analysis are also reported for you, including the torsional rigidity for each direction. The rigidity used for the torsional analysis is going to change depending on whether you have selected capacity or deflection-based distribution in the Design Settings tab. For the forces summarized in the log file, they are going to be summarized based on blocks. When it comes to wind loads, you will be able to match the reported pressures in the table with the unfactored loads in plan view. The loads in the log file have not yet been factored down to ASD level. If you'd like to complete your own checks of the wind load generation or seismic load generation from the log file, it is possible to transfer the information from the log file into an Excel spreadsheet. Here are the general instructions. The log file will need to be saved as a .log file, so you will need to modify the file type to .txt. Next, open Excel. Go to the file browser, change the lookup file type to text, open the save log file. A wizard will appear, and you are going to want to delineate the file based on spaces. Click Finish in the wizard, and the information from the log file will be transferred into an Excel spreadsheet that you can modify and check as you desire. In this slide, we will discuss how the wind pressures generated in the log file are distributed to each story as line loads. In the next slide, we will go over how line loads are distributed to each shear line within a story. In this case, we're looking at a two-story structure with a flat roof. On the first story, there is no wind load generated on the bottom half of the wall, and it is assumed that all wind loads on the bottom half of the wall in the first story go directly into the ground. For each story, the wind pressures are split in half at each story. In case of this file, we have P1, P2, and P3. For each of these pressures, a different reference height Z is used to determine the pressures. So P1, P2, and P3 will all have different magnitudes. Since line loads you can see in plan view on the first story would be determined by summing up the pressures from half of the first story and half of the second story. So in this case, L1 is equal to P1 times the height of H1 plus P2 times height H2. On the top story, half the pressure from the story, P3 times the height H3, would be used to calculate the total load on that story. If there was a sloped roof or a roof in general, the roof pressures would also be added to the top story. Now that loads have been distributed to each story, we will go over how these forces are distributed to shear lines within the story. In this case, I've turned off the display of the wind loads going in the north-south direction, and we will only discuss the loads going in the east-west direction. I recommend utilizing the Loads and Forces tab when viewing loads. In plan view, some loads are unfactored and some are factored down to ASD level. I recommend looking at the legend if you are unsure about what level of load is displayed in plan view. For wind loads, both the unfactored windward and unfactored leeward loads are going to display in plan view. But when you review the loads which are distributed to each shear line, these loads have been factored down to ASD level. The factored shear line forces are determined by summing up both the unfactored windward and unfactored leeward loads and then factoring them down by 0.6 to ASD level. The amount of load going to each shear line is going to depend on the type of diaphragm distribution, either flexible or rigid. In the case of this example in the slide, the flexible diaphragm distribution is selected. and there are only 2 shear lines, so the total factored load is distributed evenly between the 2 shear lines. It's worth mentioning that the lateral loads used for shear design are cumulative, so the shear line is going to include additional factored loads from the stories above if there are any stories above it, or shear lines. Now for a little discussion of uplift and parapet loads. In any project file, the first time you click on the Loads and Forces icon, the following warning is going to appear, which warns you to add additional loads manually to account for the effects of dead loads, wind uplift loads, and loads due to parapets. Shearwalls cannot account for the orientation of the framing in the roof or floor diaphragm, so it is necessary to add dead and wind uplift loads manually to shearwalls. Dead load to resist overturning will decrease the forces imposed on hold downs, but typically the contribution from dead load is not very high, and not including the dead load would create a conservative design. Wind uplift loads should also be applied to the top story of a structure, and realistically wind uplift loads are really only a concern for one-story structures, since the dead loads from the multi-story structures will likely counteract any loads due to wind uplift. There is an existing feature request to include parapet design in shear walls, but until that feature can be completed, it is necessary to account for parapet loads yourself by manually applying loads. It is possible to add seismic, wind, shear, and wind component and cladding, wind uplift, dead loads, and building masses into a project file. You can add these loads as point, line, or area loads. ASC 710 provides guidance on generating both wind uplift and wind loads due to parapets. Wind uplift loads are going to increase the overturning forces along shear lines, and wind loads due to parapets are going to contribute to the total lateral load at the top level. We're going to move on to a demonstration of adding wind uplift and wind parapet loads to a shear line in an example project file. This is just a 2-story structure with a flat roof, and I'm already located on the second story. The best way to review loads that have been generated by the program and to add loads is to go to the Loads and Forces tab, which I'm already in. You can see the form view associated with it. So here you have a summary of all the loads that have already been generated for this structure based on the automatic load generation. And we're going to start by adding a wind parapet load to all 4 faces of the structure. So to do this, you have 2 options. You can either go right to clicking the Add button and specify where you want to add it right in there, or you can actually click on a specific wall and then click the Add button. So this is automatically going to set up that I want to add the load to the building face, in the south building face in this case. So to determine your the parapet load, for the purpose of this example, I'm just going to use a 10 PLF load. And you're going to see that the load here on the south-facing wall is going to become 97.9 PLF once I add this load. In terms of the type, I've gone with a wind shear since we're adding an additional lateral load. I'm going to use a line load to add it to the project file. You have the choice of adding it as a factored load or an unfactored load. In this case, I'm going to leave it as an unfactored load. This way it'll contribute to my total load here and then be factored down when going to the shear lines. So building face, magnitude is here. Ultimately, the wind direction. You need to decide whether or not this is going to be a leeward or windward or both ways. So when you're looking at a parapet, there is a leeward and windward load acting on it. So in this case, I'm going to go with both ways, assuming that I've summed up my leeward and windward load. And the total of that, it would be 10 PLF acting on the wall because of the parapet. Down here you have the distribution method. I'd recommend leaving this as both. So now that we've filled in all our criteria, I'm just going to go ahead and add that load. You can see right away that that load has jumped up to 97.9. So the same procedure would be, you could follow the same procedure for the other 3 walls, building face, east, 10 PLF, both added as both ways. Okay. Same thing with this face, add both 10. Okay. and here, add. Okay, so so all these loads are going to increase the factored loads that these shear lines are going to see once the design is run. Now for the uplift load, like I mentioned before, the reason that we don't automatically apply uplift loads is because we don't know the orientation of the framing. And ultimately you're going to need to decide where these uplift loads are going to exist. In case of this example, I'm only going to add uplift loads to lines A and B, assuming that I have all my joists or rafters or whatever my roof system is spanning in this direction, so that all the reactions end up on these two shear lines only. So you have the option of clicking on the shear line first and then going to the add button, but I'm just going to go right ahead and click the add button, and in this example change the type to wind uplift, still a line load I'm going to use, and I'm going to apply it to a specific wall line, in this case wall line A from 0 to 40. And once again, the 10 PLF, this is just an example. Like, you would obviously have to perform your own calculations to get the correct load. So once all that criteria is done, press OK, and then right away you can see that 10 PLF wind load, uplift load has been added. I'm going to perform the same task on the other shear line here, shear line B. Add, change it to line B, 10 PLF, and press OK. So if you were to run the design of this project file and navigate using the go-to table to the wind flexible hold down design, you scroll down a little bit to wall lines A and B. Here you can see all the the uplift loads that have been created based on that 10 PLF load that I added on both those wall lines, and you can see that they are being combined into the total overturning force calculation. And if you did have some dead load applied to the shear line, it would actually reduce the combined hold down force that you need to design for. Thanks for listening.